It's kind of rain. So here's what we've got, what we have left. We basically have 3 weeks left. So this week and next week are basically going to be tied up with gas loss, thermodynamics, buoyancy, some stuff like that. Now, I did have to alter the schedule a little bit, because originally I was going to have the written final on Tuesday of that last week and then have a 3-day lab final Wednesday, Thursday, Friday. But because so many of you are taking this class for dual credit, and WotC, because they're shutting down Thursday night, I have to actually have your all grades in by Thursday night. So we're actually going to kind of move everything up a day, and like the written final will be on Monday, and then the lab final will be Tuesday, Wednesday, Thursday. That way I can have time to get everything graded and get the grades input, so for all that. And then Friday we'll just bring food and watch a good movie or something like that. So, yeah, we're just going to basically lop off a day so I can Huh?
Can we watch a Christmas movie?
No.
Please say no.
Halloween movie.
Why?
Shut up!
Polar Express.
Please
Polar
say
Express.
no.
Hot cocoa.
Please say no. Please say
Maybe
no.
Polar
That's wrong.
Express.
No. No. No.
No, not Elf.
Elf.
No.
Nat Geo Wilds, Alaska.
Ooh,
Yeah,
let's do
that's
that.
it. I'll watch it. It's good. I would do
Oh,
that.
yeah.
Okay. Yeah, let's do that.
Yeah.
All right.
Or Planet Earth or something.
Yeah, that's close enough to
Ooh.
Christmas. Blue Planet.
Magic School Bus.
Blue Planet. That's what it is.
Anyway, so if you're planning ahead,
Magic
then
school.
that's something that we've got to change based upon the schedule. Which works out well for you guys, so we get a day at the end and just kind of kick back and relax.
Magic School Bus.
No, we're
That's
not.
Magic School Bus.
This is
Oh,
Frizzle.
come on. Let's watch all the
greatest
biology
teacher of all
parts.
time. He's Miss Frizzle.
Yes,
Okay.
brain pop. Let's go.
So here's what we've got to start off with.
Oh, I should probably bring some stuff.
Something relatively simple, and that's going to be temperature. So when you look at what temperature is from the physics perspective, it's different than how, like chemistry or something, how biology tackles this idea. So basically, chemistry is, from the physical perspective, temperature is a measure of the kinetic energy of the particles that are colliding. So if you look at old school, okay, go old school, maybe back where you were in middle school, you might have like a beaker of like water, and you take that thermometer and you put that thermometer in there, and you see what happens with the level of the fluid. Y'all remember doing that old school with the thermometers? Okay. So let's say that at room temperature we're at about 20 degrees Celsius right now. Okay. And let's say that you put this into cold water. So what's going to happen to the level inside that thermometer?
It goes down.
It's going to go down. Why?
Because
The particles don't have as much energy.
I can't use mercury anymore.
They don't have as much energy. So
They don't have so much energy.
Yeah.
Okay? So basically what has to happen is this. Temperature is a measure of the direction of the flow of energy. Let me give you an example. So let's say that you take a bowl of soup, staying with the Celsius theme. Okay? And let's say that bowl of soup comes out at about 70 degrees Celsius, which would be pretty warm. Okay? Room temperature is about 20. It boils at 100, right? Okay, so 70 degrees would be pretty warm. So you take a bowl of soup and you set it out, and it's at 70 degrees Celsius. And you've taken this thermometer and you've measured it, and it says, oh, it's 70 degrees. So you leave, and 10 minutes later, one of two things is going to happen. Either the air around it has gotten cooler, and the soup has raised its temperature up to, say, 80 degrees Celsius. Okay, so you come back, and the heat energy has flowed from the surroundings into the soup. Okay, it's a possibility. I'm not saying it's going to happen. I'm just saying it's a possibility. And if you put your hands around the soup, it would feel cold because that energy has flowed from the surroundings into the soup. Temperature has gone up to 80 degrees. Huh, nice. Okay. What's the other option that could happen? It cools down, the temperature drops to 60 degrees Celsius, and the air around it would feel warmer. Which is going to be most likely to happen? Second, why? Why?
Entropy.
As opposed to the energy flowing in, the energy is going to flow out. Why?
Boy, I got it.
See it,
Matt?
I said entropy.
Kinda.
Okay.
Entropy is what?
Is it the fact that energy is trying to change forms?
Not sort of change forms, okay?
It's just spreading out.
Just,
But-
oh, yeah.
Here's what's going to happen, right? Remember, temperature is a measure of the kinetic energy. So basically, when that kinetic energy flows out, it's easier for Mother Nature, and Mother Nature will always take the path of least resistance. So Mother Nature basically says, look, well, I've got this high concentration of energy in here. I got a low concentration of energy on the outside. So I'm going to let that energy flow from a high concentration of energy to a lower concentration of energy. So Mother Nature goes, it's just going to be too much effort to take this energy that's out here and put it into the soup. Okay? It would, because then it's like, oh, well, here, you want some soup? Here, just set it outside over a period of time, it'll warm itself up. Okay? You wouldn't need microwaves or ovens or anything like that. Oh, here, we'll just put it out and it'll warm itself up. But it's not going to happen. It's always going to flow from that warmer temperature to the outside. And so one way to look at temperature is that it's a measure of the direction of the energy flow. So if you know this is at 70 degrees and your outside temperature is at 20 degrees, you know it's going to flow from where it's warm in here to where it's cold out there. Every time it's going to happen. It's one of the laws of thermodynamics. So
It's like hypo. No, what's the water? Oh, osmosis.
kind of, yeah,
Yeah.
based upon an ion, a concentration gradient.
Yeah.
Yeah. Now,
You got it.
on your equation sheet, in physics, we don't work in Celsius, we work off of a unit called the Kelvin. Okay, you have more Kelvin to develop the scale. So up in the top left-hand corner of your equation sheet, there's going to be some numbers that you're going to need for today. One is the conversion from Celsius into Kelvin. So this conversion is pretty simple. So go from Celsius to Kelvin, you just take your temperature in Celsius, and you add 273 to it, and you get, in this case, 293 Kelvin. Let's talk about the Kelvin scale. So on the Celsius scale, what happens at 0 degrees Celsius?
Water freezes.
Water freezes, right? It's equivalent to 32 degrees Fahrenheit. On the Kelvin scale, if you have 0 Kelvin, this is what we call absolute zero. Okay? So this is like a theoretical absolute, cannot get colder than 0 Kelvin. Because this actually goes back to something that Matt said earlier. At 0 Kelvin, the entropy, which is the measure of the disorder, goes to 0. So you cannot ever even reach 0. And it certainly can't go negatives. So the advantage of the Kelvin scale is this. It's never 0, and it's never negative. Okay, so this is going to play out large later on when we look at the ideal gas law. So, but here's the problem, is if you do work at Kelvin, and you say, hey, what's the temperature in your room? Which is, we're at about 20 degrees Celsius right now. If you say, oh, you know, I'm at 293, people are going to flip past that. Oh, 293, what do you mean? Okay, this is a big number. So this is why we don't use Kelvin in like your daily lives, just because people would kind of flip out. You drive by, you see the bank sign, 293 Kelvin. Whoa, you know? God, it's the end of the world. No, it's okay, it's just Kelvin. Okay, so now here's the other thing that's going to happen. A lot of times when you're talking about thermal, you're talking about a change in temperature. So let's say that you take water, which is 20 degrees, and you warm it up to 30 degrees. Okay, well that's a 10-degree change in Celsius, right? Because you went from 20 to 30. Well, 30 degrees in Kelvin is 303 Kelvin. So if you have a 10-degree temperature change in Celsius, that's also a 10-degree temperature change in Kelvin. So Fahrenheit gets weird because you have to multiply like 5/9 and add 32 to get to Celsius, and then you have to change that into Kelvin. So that's why we don't mess with that. So this is the beauty of this in terms of changing temperatures. So if you have a 10-degree temperature change here in Celsius, you have a 10-degree temperature change here in Kelvin. The other advantage of it is that you'll see why this is important later on. You don't get negative numbers and you never reach 0. So that's going to play out large later on once we start doing some calculations. Okay, so some of you may have seen this equation. Perfect. Okay. So ideal gas law equation, right? Now we need to talk about some things here. Anybody care to guess what P stands for?
Pressure.
Pressure. Now, if there's ever a physical quantity in science that has an identity crisis, it's pressure. Because pressure gets measured in so many different things depending on basically which branch of science that you're in. Sometimes you see it in inches of mercury, millimeters of mercury, torr, atmospheres, pascals, kilopascals. Okay? If you've ever checked the air pressure in your tire, your air pressure is measured in what?
PSI.
Stands for?
Pounds per square inch.
Pounds per square inch. Okay? So, in physics, we have a very, very specific unit of this. So, pressure at the end of the day is force per unit of area. Okay? So, in physics, that force is going to be measured in newtons, and the area is going to be in meters squared, perhaps, because it's an area. Okay? Now, to give you some example of pressure that you're under right now. So, we have this cool atmosphere. So, on a relative scale, if you take an apple and you cut it in half, and you let that represent the Earth, that red layer around the apple on that same scale is our atmosphere. Okay? That's how thin our atmosphere is relative to the size of the Earth. It's like the skin on the apple. But we kind of got to have that, because without that we don't have an atmosphere, we can't breathe, we don't have weather. Okay? We're going to be exposed to these highly charged ionized particles coming directly from the sun. So we kind of have to have this atmosphere, or basically we won't exist. Okay? Now, right now, on all of you, there's a certain amount of air pressure. Now, what's creating this air pressure?
Gravity.
Huh?
Gravity.
Well, gravity, yeah, we've got to have the gravity, because otherwise the particles are going to go flying off.
Oh, temperature.
No, kind of.
It's
But at the end of the day, what creates pressure? Why do you all feel pressure from the atmosphere? What's happening?
the atoms are bouncing off of us. There's stuff bouncing off of us.
Huh?
There's a lot of stuff bouncing off of us.
There's a lot of stuff bouncing off us. Not the most scientific explanation I've ever heard, but it works. Okay? Now, it's a lot of stuff bouncing.
Elastic collision.
Yeah, they are elastic collisions. Okay? Now, so what is this stuff that's bouncing off of you? And whatever you do, do not say air molecules. Okay? That is the most hideous term that exists in science. Okay? There is no such thing as air molecules. Matt?
I think it's air molecules.
What did I just say?
Oh, sorry, I wasn't paying attention.
Really? Santa's watching. So, just saying.
I work for Santa.
Really? One of the elves or what?
I think he's an apprentice.
Okay.
He's gonna be the next thing after he croaks.
Or the abominable snowman. All right.
Depends which that is. One of those right
Or
here.
you are more, what was it, that Yukon Cornelius from Rudolph the Red-Nosed
Yeah.
Reindeer.
Oh, yeah, that is good.
Yeah. Cornelius. Yeah. Yeah.
How do you even?
Huh?
No, he's a gold miner.
Yeah.
Oh, yeah, I just.
He's a
He wears, like,
prospector.
plaid, right?
talking
And then you
Yeah.
find, what does he come up on? Is it like a candy can, or what is it?
Yeah,
I-
candy.
All right, so enough of the Christmas stories. Okay,
Why are you still talking about?
so
Definitely how it goes.
That's
what's creating this pressure is that you have this stuff, which is mostly nitrogen and oxygen molecules that are bouncing around right now, and billions upon billions of them are hitting you every second. Okay? Now, to give you some idea of how much pressure there is pushing down on you, so here's what I did. Just stick your hand out. I'm not going to drop the bowl as well. So, right now, the atmospheric pressure pushing down on you is 14.7 pounds per square inch. 14.7 pounds is about the weight of a bowling ball. So, I'm going to take this, which has an area of about 1 square inch, okay? And I'm not going to drop this because it would hurt her hand. But this pushing down, okay, this weight of this bowling ball pushing down on her hand, that 1 square inch is how much air pressure there is on you on every square inch of your body. Now, here's the misconception that everybody has. Everybody says, oh, well, air pressure only pushes down. Well, if that was the case, okay, if air pressure only pushed down, then the bottom of your arms would be in like this pressure shadow, you know, and you couldn't even like lift your arms, you'd be like, okay? So the good thing about pressure is that it pushes all the way around. Because if pressure was only pushing down on top of the tables, so imagine that you have a bowling ball of weight on every square inch of these tables, and there was nothing pushing up from the bottom. What would happen? Yeah, everything, nothing, no birds could fly, nothing, right? Everything would just get squashed. But because of the fact that these nitrogen and oxygen molecules are moving around in a three-dimensional space, we have an equilibrium of pressure. Now, if you've ever driven up into the mountains, what happens when you drive up into the mountains in terms of pressure?
The pressure lowers.
Why do your ears pop?
Does it increase pressure, or is it decrease? Maybe it's increase. Increase the pressure.
Right? Increase or decrease?
Decrease.
I don't know.
There's a
All I know
decrease
is
of pressure.
like-
Decrease.
There's a
You kick a
decrease.
football farther in Denver than anywhere else.
Why? And hit a baseball further.
Less air pressure.
It's
Why?
whacking into fewer molecules.
Oh, I guess
Yeah,
you're
it's kind of like if you've ever seen cheerleaders build a pyramid, okay? Who's got to carry most of the weight? Person at the top or person at the bottom? Person at the bottom, okay? So, at the bottom, okay, we're here, we have all the weight of all the air above us pushing down. So, technically, when you stand up, the air pressure on your feet is a little bit more than the air pressure on the top of your head, okay? Not a noticeable difference, okay? But there is this, because of the fact that you're farther up, just like if you go to Denver, you're gonna have like a slightly lower air pressure up there. Same thing is gonna happen here.
What I don't understand is how come your ears pop when you go further up, right? But then when you go in a pool and you go down, your ears pop.
Because when you go, there's two different scenarios. If you dive deep into a pool, you're increasing the pressure.
Right.
Because you have the atmospheric pressure pushing down on you, plus the weight of the water pushing. And the deeper you go, the more intense that pressure becomes. So that's caused by an increase in pressure. But if you go up, your ears are acclimating to a lower pressure system. But in both situations, they're just trying to equalize the pressure between the inside and the
So
outside.
if you're going down like a cave, is it the same thing? Like, does that pressure increase? Like,
Yeah, but not,
is it noticeable?
No.
Okay.
no. You know, if you went in a deep cave, yeah, maybe. Okay, but then you're probably gonna freak out and get
You go
lost
in water, it's pretty useful.
Well, that's because water's so much more dense.
Give you the bends.
Ah, yeah. Okay, now, so in physics, the pressure we're going to use is newtons per square meter, which is, and this is what's on the front of your sheet, on your equation sheet, 101,300 newtons per square meter. So what this means is this. So here I've got a 1 kilogram mass, which if you round the gravitational acceleration up to 10 from 9.8, okay, call it 10, round number. So this weighs about 10 newtons. So what that means is if you have 1 square meter, so if you can visualize 1 square meter of surface area, okay, which is about 3/4 of one of these desks. That means that that's having the equivalent amount of pressure of 10,130 of these on stacked on every square meter, because that's that equivalent amount of pressure. Now you go, wow, that's a lot. It is, but we're used to it, okay? So it isn't like, oh, we live in a vacuum and then all of a sudden we're going to introduce that pressure into it. This is what we're used to. If you don't have that, and somebody mentioned the bends, bad things are going to happen. If anybody ever says, hey, let's go into the vacuum chamber, don't, okay? You have a certain amount of dissolved oxygen in your blood, which will boil, Okay? It will turn from dissolved oxygen into gaseous oxygen. The same thing is going to happen with nitrogen. Bad things are going to happen. If someone says, go, let's go into the vacuum chamber, don't. Run away and hide. Okay. So, this is also known as 1 atmosphere. Okay? So this is the most common conversion that you'll have to do. So right now you all are under 1 atmosphere of pressure. Okay, it varies a little bit. Is it a high pressure system? Is it a low pressure system, depending upon the weather? But generally, we're all usually hovering around 1 atmosphere. So this is how many newtons there are per square meter pushing down and pushing in all directions in terms of pressure. Now, interesting thing happens. So, since we're in a physics class, because these units are different in the chemistry class, so I always have to keep track of, am I giving the physics lecture of the ideal gas law, or am I giving the chemistry lecture? Because it's the same equation, but the units are completely different. So, what do you think the V represents?
Volume.
Volume. So, in a physics classroom, what's that volume going to be measured in? Yeah, meters cubed. Okay? So a funny thing happens here. So let's look at what's going to take place here. So I've got pressure in newtons per square meter, because that's force per unit of area. And I'm going to multiply that by cubic meters. So, Landon, what's going to happen if I take newtons per square meter and multiply that by cubic meters?
Wait, is that a meter cube?
Yeah, that's meters cubed and that's meters squared.
Alright, then you're just gonna have 1 meter.
And so if I multiply, what do I get? What's the other way of expressing meters?
Joule.
Joules. Oh, that's kind of cool. So the left side of the equation is joules. Because that's what we end up with, is newton meters. So if this is going to work, what does the right side have to be in?
Joules.
Joules. I can't have an equivalent statement and have this side being in joules and that side being in kilograms. Okay? I can't say, oh, joules equals kilograms. No. Okay? No. Now, we're going to focus on the inert side of this. So on the inert side, here we go. Anybody remember what the N stands for?
Number of moles.
Number of moles. So this is a flashback to chemistry. Okay? So let's talk a very brief review of moles. So let's say, for example, I ask you to measure out 1 mole of carbon. So just delving deep into the memories of your chemistry days. 1 mole of carbon is how many grams of carbon?
12.01.
12.0. Why?
Because that's its atomic mass. And you multiply, that's its atomic mass. Right? And then you have to multiply it by 6.02 times 10.
No.
Is that it?
No. Stop.
Well, that gets you
Stop.
grams, though.
That gives you particles.
Yeah.
Okay, yeah, that's the number of particles.
Isn't there some like Avogadro's
That's
number?
true.
Yes, that's Avogadro's number.
Yes, Avogadro's number.
Yes.
Okay, not avocado.
Now,
Not avocado.
so without going into an hour and a half long discussion
Avocado's
about relative
toast.
atomic mass and its history,
Avocado toast.
the number of mole is just the relative atomic mass expressed in grams. Okay, we could have done so for the relative atomic mass of carbon is 12. So we said, okay, 1 mole is 12 grams. In physics, we work off of kilomoles. So in physics, instead of 1 mole being 12 grams, a kilomole is 12 kilograms. So it's the same concept, we just put kilograms on the end of it. But number of moles, okay, whether that's, and this is what it has to be in moles in this situation. Now, so if you have 1 mole of carbon, so if I went to Bree and I said, hey, Bree, I need you to go to the storeroom and I need a mole of carbon. So she can't measure out in relative atomic mass units, but she can go to a scale and go, oh, I can measure out 12 grams all day long. Okay, that's kind of cool. So if you're talking carbon, that's going to be 12 grams of carbon. Now, how many atom carbons, or how many atoms of carbon, does it take stacked together to get you to 12 grams?
6.02 times 10 to the 23rd.
That's where 6.02 times 10 to the 23rd. That's 6.02 times 10 to the 23rd. So this is the number of atoms that you're going to have to get you to 12 grams. Okay? Now, the reason that it's this number is because each carbon atom is really small. So it takes a lot of them to get you to 12 grams. Okay? We could let it be 10, which would make the math a lot easier. But here's the problem. If you only stack 10 carbon atoms on a spoon, it doesn't have a mass of 12 grams. Because it takes this many particles to get you to 12 grams. Now, ironically, Avogadro never came up with the number. He just proposed the concept. Okay? That's all he did. He just proposed the concept. All right. So, we got that in moles. Now, on the front of your equation sheet, you have R, which is the ideal gas law constant, 8.314 joules per mole Kelvin. And we'll talk about the significance of the units in just a second. And then you have a temperature, and this temperature has to be in Kelvin. Okay? It has to be in Kelvin. It cannot be in Celsius, it cannot be in Fahrenheit. It has to be in Kelvin. And again, here's the reason why. So if you look at PV equals nRT, if you try and work in Celsius, here's the problem, okay? Like at 0 degrees Celsius, which happens a lot in Kansas in the wintertime, that's 0, okay? Well, if this is 0, that means this side has to be 0, which means at 0 degrees Celsius, either your pressure goes to 0 or your volume goes to 0, which doesn't make any sense at all because, you know, if your pressure goes to 0 when it freezes, your car tires would just deflate because of the fact that there wouldn't be any pressure inside your car tires at 0. It'd be weird. Worse yet, you have no volume. Your volume goes to 0. It's like, it's going to freeze tonight. It's going to get down to 0. What's going to happen to the volume of your tires? They're going to go to 0. That's going to be awkward. Okay? But as soon as it warms up, they reappear, and then we have volume. Okay? Worse yet, if you have a negative number, like it's like negative 3 degrees Celsius,
Negative pressure.
yeah, you either have negative pressure or negative volume, which is even weirder. Okay? It's like not only are they gone, they're negative. Wow. So that's the advantage of the Kelvin unit, is that you don't have to worry about this being 0, and you don't have to worry about negative numbers because that's just going to get all wonky. Now, here's the beauty of this. When I take joules per mole Kelvin, and I multiply it by moles, and I divide it and multiply it by Kelvin, what do I get?
Joules.
Joules. Wow. Guess what? That's going to match up with the PV side. That way both sides are measured in joules. Okay? Now, if you're in a chemistry class, that pressure is in atmospheres and the volume is in liters. And you use a completely different value for R. You use like 0.0821. Okay? So in chemistry, it's the same concept, the same equation, but everything's in different units. Okay? The temperature is still in Kelvin, but this is in liter, that side is in liter atmospheres, so this side has to be in liter atmospheres. So that's the difference. Okay, now let me prove to y'all that you all understand this equation. So give that a spin. So in here I've got a vacuum chamber here, and got a piece of tape. So I'm just going to secure the balloon to the top. So here's the question: on an atomic level, what's giving shape to the balloon? What is happening inside that balloon that it has a shape?
The air molecules.
What are they doing?
Bouncing off each other.
And what's bouncing? Olivia, what's bouncing?
Molecules.
Of?
Not of air.
Not of air.
Of oxygen and nitrogen.
Which one is higher abundance, nitrogen or oxygen? Yeah, nitrogen. Well, we're about 77% nitrogen and about 22% oxygen. If it was the other way around, if we had like 77% oxygen and 22% nitrogen, fires would burn completely out of control. Then you would never be able to shut down a fire because of the fact that it would be in such an oxygen-rich environment. So it's cool that we have we have enough oxygen to sustain life, but not so much where we can't shut down a fire if we have to.
So are those
Okay.
oxygen tanks bad for you?
Huh?
The oxygen chambers, are those like not that good for you though?
Well, your body can only absorb so much oxygen. But the problem with oxygen chambers, if you ever start a fire,
You're dead.
yeah, basically, that's what happened like on the Apollo 1 missions.
Mm-hmm.
Okay, so inside this balloon, imagine that you have all these little second graders named Timmy, okay? And they're bouncing around. And we're going to explain a lot of thermodynamics with little second graders named Timmy. So inside of here, you got all these little Timmies going, "Ah!" Okay? They're bouncing around. Now, is there pressure on the outside as well?
Yeah.
Yeah, because we have an atmosphere. That's kind of cool, right? Okay, without it, we're all kind of screwed. So I'm going to take this, put it on here, and then I'm going to begin to draw the air out of the chamber. So there's three things could happen to the balloon. It could just stay the same size, because I'm not going to change anything inside the balloon. It could get bigger, or it could get smaller. Mary, bigger, smaller, stay the same.
Let's say smaller,
Why?
because, I don't know why.
If you increase the pressure,
Just because.
Yeah,
Just a gut feeling.
yeah.
Okay,
if you increase,
great.
If you decrease the pressure, then the volume of the balloon has to go up,
Why?
because they're directly related.
They're directly related. As one goes up, the other one goes up.
Wait, maybe that. Oh, wait, no, they're indirectly related. I think. Wait, no, I think they're directly related.
Landon?
I'm gonna go with the what's like molecules and stuff on the outside. It's easier for the stuff on the inside to push out, so you got more volume.
Yeah.
Okay, so you're saying because there's going to be a smaller number of Timmies on the outside
Yeah.
pushing in, the same number of Timmies on the inside trying to be free,
There we go. Yeah.
be free. Okay? Anybody who's just going to say the same because we're not going to change anything?
No.
Okay? All right, so let's see what happens.
my arm's getting tired.
Got bigger. So as I decreased the pressure, the volume had to go up. Okay? Now, this is what, if you look at where biology meets physics meets history. Okay? In World War II, we had a huge bombing raid in Germany. There was two primary long-range bombers that the United States flew. There were B-17s Flying Fortress and the B-24 Liberators. Both of those were non-pressurized cabins. Okay, these were high-altitude bombing rates, so you're up to like 30,000 feet. Very, very cold, and a very, very low pressure. Okay, so this is important. So one of the things that they had to do with the bombing crews was they had to basically ban them from eating beans. Why?
Because it
What
makes
do beans do?
make gas.
They create gas, right? So imagine this is your intestine at 30,000 feet, where you have a small pocket of gas. You have a lower atmospheric pressure. What's going to happen to the volume of gas inside your intestine?
It's gonna get bigger.
It's going to get big. Guess what? That's going to hurt a lot, okay? Because they weren't pressurized cabin. If you've flown in in a modern jetliner, hey, it's a pressurized cabin. You can't tell any different. Flying at 30,000 feet, if you're a non-pressurized cabin, this is what's going to happen to any gas that's inside your intestine. It's going to expand, which is going to be very, very painful and very bad. So it's like, okay, hey, great, we're on a bombing run, being shot at by German Luftwaffe planes, and I'm doubled over in pain because of I had Mexican food for lunch. Okay, so they didn't want that to happen, and so they regulated the diet of the bombing crews because they were at higher altitudes. Now, when they got back down to lower altitudes, oh, hey, pressure increased, pain went away. But that was one of the lessons they had to learn. So if I release this, and let that pressure come back in, okay, then it's going to return back to that normal size. So now the pressure on the inside is going to be balancing out that pressure on the outside. Okay, got that idea. Okay, so watch out. Here we go. Back here. Okay, so what I'm going to show you is how you can work any gas law equation. So if you look at what happens here, so we have pressure 1, volume 1 equals nRT equals pressure 2 volume to. Okay, so here's what we had going on. When I altered the pressure, did I change the number of moles of gas inside the balloon?
No.
That stayed the same. Did I change the gas law constant?
No.
No, it's constant. It really doesn't change much, that's why we call it constant. Did I increase or decrease the temperature of the particles inside the balloon?
No.
You didn't mess with the balloon.
I didn't mess with the temperature, right? I didn't mess with the temperature. So this whole thing stayed the same. So here's the idea, is if pressure 1 times volume 1 equals inert, and pressure 2 times volume 2 also equals inert, this is like if A equals B and B equals C, guess what?
A equals C.
A equals C, otherwise known as the,
Oh,
runs with transitive,
transitive.
transitive property, okay? Y'all, do they still make you do proofs in geometry?
Yeah.
Oh,
it's
yeah.
terrible.
Proofs?
It's the
Oh,
worst.
they're horrible.
I was just pleased. Yeah.
Yeah, proofs are dumb.
I honestly don't know how.
They're god awful.
And I think that's the most emotion I have seen out of you this entire class.
I have a lot of emotion about proofs.
And none of it good.
No.
None of it good. Okay.
Let my work stand. I don't have to prove it. Yeah.
So basically what we've got is that we have P1 V1 equaling P2 V2. So here's the situation, right? So what we started off with was a relatively high pressure and a small volume, right? We had high pressure relatively. So then, when I created a vacuum, what happened to the pressure inside the chamber?
Decrease.
The pressure became smaller, so to equalize everything out, the volume had to become bigger. So that's why there's an inverse relationship between pressure and volume. Okay? Cool with this. Now, typically on 99% of gas law problems, 99% of the time, you don't change the number of moles, nor do you change the gas law constant, 99% of the time. So if you isolate that by itself, what you get is what's known as the combined gas law. And this is kind of like the mother of all gas law equations. So you have P1 V1 over T1 equals P2 V2 over T2. So basically all I did is I took PV equals nRT and I divided this temperature, so that way I've got nR, and that's going to be the same in two different conditions. So here's the beauty of this. If you just remember this, you can solve 99% of gas law problems, even if you're holding a couple of things constant. So if you look at what we did, P1 V1 equals P2 V2. So since my temperature stayed constant, I don't have to worry about the temperature part of it because I didn't change the temperature. So that just leaves me with P1 V1 equals P2 V2. Now, when do you think you're going to be most likely to get like a low pressure indicator light on your tires, on your car?
In the winter.
In the wintertime or in the summertime?
Winter.
Cold.
Why, Bree?
Temperature goes down, pressure goes down because they have like a direct relation.
Okay? Now, so here's how you can explain this in terms of like Timmy's, okay? Second grade Timmy's. So what creates pressure is Timmy running up and then bouncing off the walls, right? So if you've ever seen Timmy's second graders outside on a cold day, by the way, did y'all, any of you like were in the same class in like grade school or anything?
Yeah. You lie.
Really? You two were in the same class?
Me and Eric?
Yeah, dude, Eli and I used to be
Yeah, we
best
were really good
buds.
friends.
Really?
Yeah.
Yeah.
Okay.
And Garrett was my neighbor, so we used to hang out too.
Okay.
Eli used to bully me on the basketball floor.
Oh.
I'm not gonna deny it, but I don't remember it.
He didn't let me play with the big kids.
Yeah.
Really?
I did.
Okay.
And Felix bullies you now.
Okay, now, so when it's cold outside, what do second graders do?
They sit there and
They
scream.
They cry.
They tend to huddle. Okay, let's go with Olivia. They
go up
huddle.
to
It's
the
funnier
corner of the
now.
building, and then the person in the middle is like the warmest.
Yes, kind of
Trying
like
to get out of the sleep.
Okay.
That's what I would say.
So they don't occupy
love
much space,
That's a
right?
great-
Now, if you imagine like the confines of the classroom wall being like a balloon. So if it's cold inside, the second graders are going to be bouncing off the walls, but if they're pretty chilled out, right, they don't bounce off the walls very much, so you don't get a lot of pressure. Now, as you increase the temperature, which for second graders would be giving them each like a bag of Skittles, okay? You give them each a bag of Skittles. What's going to happen to the pressure inside the room?
200 degrees.
Oh, it's going to increase, right? Because now they're going to have more energy. Now they're going to be bouncing off the get Skittles, okay? And they're going to be bouncing off the walls, okay? So, as you increase the temperature, you increase the kinetic energy of the particles, they're going to bounce off the walls more frequently, and they're going to have more kinetic energy when they do it. So, if you look at holding the volume constant, okay, so if V1 and V2 are the same, in other words, your car tires volumes are basically stay the same. So then if we do a little cross multiplication, we get P1 times T2 equals P2 times T1. Now, let's look at what Bree said, okay? So when it's warm outside, okay, let's start over here. If it's warm outside, what do you know about this temperature? Big number, small number? Big number, right? Okay? And then over here, I'm going to have a, when it's cold,
Small.
that's going to have a smaller temperature. Now, so if these sides are going to balance out, then with what's going to happen to this pressure over here? Big pressure, little pressure.
Little pressure. Wait, yeah. It's gonna have to be a small pressure. Wait.
Big pressure.
Huh?
You increase the
Okay. So at high temperatures, right, you're going to have,
Yeah.
so P1 over here is going to be
Whoa.
big.
I
So
got
that
it.
means pressure 2 over here is going to be small, okay? Because the pressure, because when you look at this, what's going to happen is that when you have that lower temperature, this is when you're going to have a lower pressure because of the fact that the particles aren't going to have as much energy to bounce around. At a higher temperature, you're going to have a higher pressure because you're going to have two things happening. You're going to have more collisions because Timmy's moving around more often, and Timmy has more energy when he hits the wall. So you have two things happening when you increase the temperature to make that pressure go up. Now, visualize this. And this is a situation where you all intuitively understand what's going to happen. So ladies, don't, if you ever date a guy that says this, run away. Here, let me show you my syringe. Okay? Unless he's diabetic. But other than that, run away and hide.
I'm diabetic.
Just a word of advice. Okay? Not necessarily set in stone, but just saying. It's like, why do you have a syringe? I'm a physics teacher. Whatever. Okay. So, I take this syringe, and I'm going to push in on the plunger. Okay, that was disturbing. Okay. You're over here.
Hey, do you need a bell?
No,
he's
get
got a
out,
tie.
wrapping it around. Okay.
Why not?
Okay. So,
Your belt.
okay, so I'm going to take this, push this in.
Your finger's gonna
Now-
get stuck to it.
Am I doing work?
Yeah, push it away.
Yes, force over distance.
Why?
Force over distance.
Yeah, I'm exerting the force over distance. You'll see that work also plays a vital role in this whole discussion, okay? So I'm here, I'm going to take this, push this in. I'm going to do work. So what do you think is going to happen to the pressure inside the syringe? Increases. Why?
The volume's out. Your finger's not letting it get
The
out.
volume's decreasing. And you're doing work, so you're creating energy, so that has to be transferred into the syringe, which increases pressure.
Okay, now imagine this is second graders, okay? Imagine that
I was doing the math in my head. I was using an abacus. You ever do that?
no. Okay. Yeah, okay. So imagine that, God forbid, that I teach second grade. Oh, no, it wouldn't. No, it wouldn't.
He was
I'd
throwing
get
kids.
the first day, half the class would be crying.
He was throwing
Good.
Okay? Not intentionally.
They need to learn
but it's like,
lessons.
you sit down. All right. No, that's just not going to end well. Come here, Timmy.
Separating.
Are you going to tell your mom about this? No. Okay. All right. Oh.
Let's all threaten some second graders.
Yeah.
Let's all threaten some second graders.
No.
My little brother's in second grade. Do you want to go
No.
talk to him?
Okay.
Can I bring a fourth grader?
No, I'm good. Trust me. It's just, I can't even handle freshmen, okay? No. They're just like, they're just nasty. Okay. They're just snot-nosed. Okay. Anyway, with that said, so, they just have no sense of humor either.
Yeah, they're not quite there yet.
No, they're not. You know, if I
you could say something and then they go home and tell their parents and
I know, it's like,
They'll
Mr.
get
Burkamp said, it's talked about marijuana. What is that, Mom and Dad? Okay.
Dude,
It's on the
come
video.
on.
Anyway,
It's so hard.
Backward, like,
I'm teaching one lesson about
stitches
snitching.
get stitches.
Pick them up by the head.
Yeah, you gonna tell
This is
your mom
what
about
you
this
get
one?
for telling your mom about America.
Okay, anyway.
What's the
Anyway.
kids, I want to tell them.
I
So,
do that on the day.
when I do work, back to our story of the syringe. So, when I press this in, so imagine taking the second grade classroom and confining the space. What's going to happen to the number of collisions? It's going to increase because you're going to have more. You're going to have the same number of little tinnies bouncing around, but now they're going to be hitting the walls more often. Okay, so now if you take that same classroom and you expand it, though, what's going to happen to the number of collisions? It's going to become less because they're going to have more space to move around. So pressure is basically the number of collisions that happen with the side of the syringe, the classroom wall, whatever that may be. Got that? Okay. So we're cool with this. Now, let's see what temperature can do back here. So another application. So come on, back here. Yes!
What the heck?
What?
This thing was at like 95 minutes when I plugged it in, and now it's only at 86.
No, right here. Right here.
Yeah. It's fine. Wow, you're so tall right now, Mary.
Max is
No, she's not. I don't think so. You're like the same size as me.
Okay. So,
I know a guy.
yeah, we got.
That's a good point. Can I get a better
Okay,
angle from
so
over
let's
here?
say that I want to
Okay, thank you.
strike a match. Okay, so what do I have to do?
Strike it.
Do work.
I've got to do work. And what are the two components of work? Because if I just apply a force, what's going to happen?
Nothing.
Well, yeah, but am I going to light it? No. No. And if I just do a distance, okay, that doesn't do much for me either, okay? So I got to kind of combine both. But what else has to happen?
Friction.
Friction. Now, what if I do this very, very, very slowly?
They'll create some, but not enough,
Create some, but not enough. Why?
because it's not fast enough.
So if I go faster, what am I type of energy am I increasing?
Kinetic.
Kinetic energy, right? So if I strike this really fast, I'm going to generate a lot of kinetic energy. So this is what's known as, to start any chemical reaction, there's like a certain threshold of energy that you have to cross called the activation energy. So if I just go across very, very slowly, I don't cross that activation energy. So the activation energy is like the first big hill on a roller coaster. So you've got to get up and over that hill. So if I don't go fast enough, I don't get the reaction up over the hill, and I don't like the match. So turn this on, get this go. Oh, come on.
Faster, bird.
More force.
There she blows.
Okay, we have fire. Okay,
Wait, it's blue. Doesn't it look cold?
huh?
I was making a sarcastic comment.
Okay. So what this is two thin pieces of metal laminated. So when I put this in the fire, you'll notice that it bends. So when metal heats up, do you think it expands or contracts?
Expands.
Expands. Why?
Conductors, so it's gonna.
Yeah, the little tip gets to bounce around more, right? So I got two different types of metal. So which metal do you think is expanding at a faster rate? The one on the outside that's pushing it over, or the one on the inside that's curling under? Outside, right? Because it's trying to expand it, it's expanding faster. This one on the inside isn't as expanding as quickly, so therefore it's pushing it in this direction. So if any of you have like the old style thermostats in your house, where it's like the little slider, okay, have you ever seen those? Okay. Basically what happens is inside that thermostat, there's a piece of metal like this. So as the temperature in your house changes, it changes the pitch of this piece of metal. So where you set your thermostat, let's say it's in the wintertime. So as your house cools down, that piece of metal is going to flatten out some. So once it cools down and it flattens out, then it's going to come in contact with the thermostat. It's going to complete the circuit. It's going to send a signal to the furnace that says, oh, we need to work. House warms up. Then as the house warms up, that piece of metal then bends back down. It loses contact with it. Then you break the circuit and the furnace shuts off. So where you set your thermostat is where you're going to make contact with that piece of metal. So each metal has a unique expansion rate. So based upon that idea, I got this set up. So this is all brass, so everything's going to expand at the same rate. So I've got this one, which will fit just inside of this gap, okay? So what I'm going to do is I'm going to take this and I'm going to heat this up. So once I heat this up, what should happen to this?
It shouldn't.
Shouldn't fit. Why?
Because it expands.
Too big.
Because it expands, right? So all of those little particles, electrons, protons, and neutrons in there start freaking out and vibrating a lot more, right? And you're going to occupy more and more and more space. Now when I try and do that, now I can't get that in there because of the fact that it expanded enough and it was such a tight fit that that will no longer fit in there. Now I'm going to let this cool down a little bit. And then I'm going to take this, and here's the other side of it. It's got this hole here. So I can take that, and I can get, it'll go in there, but it's a really, it's a pretty tight fit, okay? Pretty small machine fit. So what I'm going to do is I'm going to warm up this side, okay? So I'm going to warm up the side that has the hole in it. So there's three things that could happen. The size of the hole doesn't change at all. The size of the hole gets bigger, the size of the hole gets smaller. So,
Gonna grow.
It gets smaller. Boom.
why?
It's like expanding, but
Oh,
the hole
yeah,
gets
that makes
smaller.
sense.
Okay?
There's no brass in the circle.
Ah,
Okay.
it's good.
So how many vote that after I heat this up, that, because this will barely fit in there, okay?
gotta keep
That
it
after I
steady
heat
here.
this up, that it won't fit in there. That this is going to close up and I won't be able to put it in there.
I cast my ballot now.
Okay? How about this just going to stay the same size? How about it's actually going to get bigger? Mike was on the big train.
Yeah.
Okay? All right, so let's heat it up.
Big train.
I want Michael to be right.
Felix.
I mean, I don't think he will.
Michael's gonna own us all.
But you want him to be, I don't think he will, but you want him to be right.
Dude, I can't do that smell anymore.
Dude, I'm
getting lightheaded.
Okay? So I got this pretty hot, right?
Catch me.
It actually
Oh.
fits.
Michael's right.
Michael's right.
Wow. Oh.
I know, and then you got talked out of it. So here's the deal.
Wow.
Last time I listened
Michael
to
owned
Landon.
us.
Okay, but no, intuitively it makes sense. You'd say, well, it's going to expand to it and push that further in. So here's the issue, or here's one way to look at it. Imagine that I had cut that piece out and I put that piece back in and heated it up. So if that had actually been a solid piece and I heated it up, which direction would it expand? It would expand outward, okay? So by virtue of the fact that that's not there, and nature's always going to do what's easiest. So if you've ever worked with metal, it's much easier to take a metal ring and make it bigger than it is to take a metal ring and try and compress that thing into a smaller diameter. It's always easier to make it bigger. So this fits in there easier because of the fact that when it heats up, that hole expands from the inside to the outside. And that's why that's going to fit like it does. Okay? Got it? Good? Back we go.
Ah, darn it.
What?
I don't know, fire.
You know, just realized that Max is the gyroscope one.
Yeah, well, he put it somewhere. He put it over there on the cabinet when he put the solar panels up.
Okay.
Wait, is it just lecture notes?
No, these are physical concepts.
Eli. Dude, I can't.
So, Mr. Burkhead,
What?
do you like buildings expanded that are made out of metal but have no parts in them? I get. So, like,
Huh?
yeah, like the Eiffel Tower. Does it,
A few inches
when it gets
taller
hit
than
by
the
the
sun.
sun, does it expand?
I did the whole.
Yeah, it's a few inches taller than the sun.
I'm just trying to. So like when they built like the arch in St. Louis,
Yeah.
they built it with such precision that last piece they put in was the piece in the middle, and they had it calculated with a certain temperature. And so right as they went to put that in, the sun came out and it heated up the metal, and that metal expanded enough that it closed the gap where that centerpiece wouldn't fit. So they had to take fire trucks and spray water on both sides of the arc to cool it down so that centerpiece would fit back in.
That's what I was wondering, if that would mess with, like,
Yeah, oh yeah, oh yeah.
oh no, is that the homework?
Is that why they keep some plane parts frozen before they put them in?
Yeah.
That makes sense now.
Well, and the same thing what they'll do with bearings. So, bearings have to slide over like a shaft. So what they'll do is, if they want a good fit, they'll machine that bearing where they'll take that bearing and put it in hot, like boiling oil, and that'll expand the size of that bearing. They'll put it on, and then as it cools, it locks itself on that shaft. Wet?
Come on. I don't like it. 50-cent piece.
Okay, so let me go over this sheet here. So down here on this page where it has values of thermal expansion coefficients, notice that you've got like brass, brick, copper, iron, steel. Now, down here below are some equations that are going to make life for you simple. So what this shows you is how much the thermal expansion takes place. So let's look at L equals L naught T, and then you have area equals naught. And volume is Now, here's the odd thing about these. When you look at these values of thermal expansion, they have weird units, because the units on this are Celsius to the -1, which is like, whoa, it's like the inverse of Celsius, which doesn't make much sense. But here's the deal. So if you look at brass, which is what we just worked with, so brass has 19 times 10 to the -6. So here's where this is kind of cool. Whatever units you have here, this length could be in inches, centimeters, feet, doesn't make any difference. This is just going to be some unit here, okay? Some unit of length, some unit of area, some unit of volume. So you have alpha, which for brass is like 19 times 10 to the -6, and that has units of Celsius to the -1. And then you have a change in temperature, which might be like 80 degrees Celsius. Now, here's what's important. Listen to me, people. Listen to me, listen to me, listen to me. This is not the temperature of the metal. This is the change in temperature of the metal. It is not the temperature of the metal, okay? It's the change in the temperature of the metal. So what this means is if you have no change in temperature, guess what? Your final length is the same as your initial length. So the bigger the change in temperature that you have, the bigger that length is going to be. So here's why this works. This is Celsius to the -1. This is in Celsius. This cancels out. So the only units that you have, or whatever L naught is in, area naught, volume naught. Now, why do you think in area naught, why do you think this is 2, and why in volume do you think there's a 3?
Squared and cubed.
Yeah, okay. your area will expand in 2 dimensions, your volume will expand in 3 dimensions. And that's why those values are there. So here's what you have to be careful of. So when you get to like question number 13, it's like, what's the change in area of a brass that's 20 centimeters on an edge and the temperature changes by 80 degrees Celsius? So I don't care what this is. You can leave this in square centimeters, you can change it into square meters, I don't care. It doesn't make me any difference. It's all going to work out to be the same. But here's what you have to be careful of. This equation will get you the new area. Okay, so if you just plug these numbers in, this gets you the new area. But the question is going to ask is what's going to be the change in area. So you're going to plug in A naught, and then that's going to calculate the new area. So to get the change in area, you've got to subtract that final area from the initial area, because that's what it's asking for, is the change in area, or the change in volume. So because what this will get you, what these equations will get you, is the final volume, the final area, and the final length. So that's what you have to be careful of in terms of what it's asking you to find. Okay. Anyway, now to make sure everybody's cool, on number 10, you got 0.45 grams of helium. How are you going to convert 0.450 grams of helium into moles of helium? What's going to go down here? No, not 1 mole. You're going to have 4 grams because the molar, and I tell you this in the problem, the molar mass of helium is 4 grams per mole. So are you going to have more than a mole or less than a mole? Less, because you'd have to have 4 moles to have an entire mole. So you got 0.45, so take 0.45 divided by 4. Now, on these temperatures on the gas laws are in Celsius. What are you going to have to do with all those temperatures in Celsius?
273.
Change them into Kelvin, add 273. Okay. Yeah, we're done.